Can you see the presentation well?
Yes, sir.
Good. So let me go through the statement. I will explain some practical issues, and I will ask you to write down some data that we will need later. Okay? So this is the general structure, which is, as I mentioned, we will have to say something about the floods, the previous pool level, gate performance, the maximum pool level, the non-failure, the failure modes, and the consequences. But we are doing a simplified model, which is it will look like this. We will ask the software to create a model in which we have to only care about overtopping failure. So we need floods, normal operating level, how reliable gates are and how many gates we have, the flood routing, a fragility curve, and a break hydrograph with damages, economic damages, and loss of life. And so we can compute the incremental damages and incremental loss of life. But the architecture is well prepared for this one only failure mode, which is overtopping. And that is how our model is going to look like. Okay? And it will be a gravity dam. And we need to write down these three numbers because that will be useful later. So crest level at 1,083 meters over sea level, above sea level. Normal operation level, 1,077.97. And base level, the foundation level, better say. The foundation is at 1,026 meters above sea level. If we write these three numbers down, that will be helpful, so we don't have to reopen the presentation later. So another thing, return periods, because we had paleo flooding and we had a very detailed, supposedly, a very detailed hydrological study, ranges from 1 year period, return period to 100,000 years. Remember or write down the whole range of known hydrographs span to 100,000 years. That means that the software is going to compute all these intervals, which I have there. You don't need to worry about this because the software will break the branches in a number of intervals doing something like this. And for the last interval, whatever is farther to 100,000 return period years, it will assume 1 over 100,000 years, which is 1 to the minus 5 will be the remaining probability to the right. So when the software adds all these, and it will do it automatically, the total annual probability of exceedance will be 1. So it will be computing the full range of the hydrological loading. This is a little difficult to understand if it's the first time you are doing it. I think it is very well explained in the manual, and I don't want to spend much time on this. I'm going to ask you to believe and go to the manual and check how the software splits the range of loading in a way that altogether the annual probability of exceedance, the total annual probability of exceedance is 1. So the full range of loading is computed. So then the water level, we need the water level in the reservoir when the flood arrives, and we are assuming that it will be the normal operating level, that the reservoir is basically always full, which is the case when you have a lot of water and hydropower reservoirs. they tend to be full or very close to the normal operation level. So that will be our assumption. Then we will need to assess the reliability of the gates. But the software offers us verbal descriptors, and you will see that our gates have had in the past some problems when trying to open it. That means that their individual reliability is set to 75%. That means that once every 4 times we try to open the gates, we were not able to do it. So we have dangerous spillways. And how it computes the probability when you have more than one gate, which means if you have, for instance, 2 gates, there is a probability of functioning 0, 1, or 2 gates. You know that the individual reliability is 75%. The way the software adds probability to the 0, 1, and 2 possibilities is using a binomial distribution and doing exactly what this equation says. You can review what it means. I don't think we should go into the details. It is also well explained in the manual. So in this case, what do we have to write down? We have a spillway, a surface spillway with 2 gates, a bottom outlet with only 1 gate. And both of them had problems, so the individual reliability of each gate is 75%, as I anticipated. So write this down, because we will need to incorporate this to the software manually. Okay? Or if you don't want to write it down, you will have to have this presentation open. So we need to do the float routing, which means for every return period, and depending if you have bottom outlet working or not working, and a spillway working properly, 0, 1, or 2 gates, we need to do what I call a parametric routing. It looks like this. For instance, this is for return period 100,000 years, annual exceedance probability 1 to the -5, normal operating level, which is the pool level, always at normal operating level. And for instance, this is when the surface spillway doesn't work and the bottom outlet doesn't work. Then we know what is the maximum water level and the discharge. That you do for all the combinations and for all return periods, but we don't need to do it. In one of the Excel files that I sent to you, this is done already, but it's done for all the combinations, and we will just upload this routing Excel file. So as the more things we need to write down. As the failure mode is overtopping, we need to know when the overtop starts. So it starts at the crest level. And remember, we have said the crest level is at 1,083 meters over sea level, and it is a gravity dam. So the fragility curve will be also offered by the software, which is a generic based on experiences, and means that with 25 centimeters of overtopping, probability of failure is 10%. But with 1 meter of overtopping, probability of failure is 100%. And this is the shape. Of course, this is a simplification, and it's based in case histories. But we are using these as our fragility curve, because we don't want to say that just because we overtop over a gravity dam, it fails, which will not be true, and it's not scientifically based. So this is a simplification, but it's a simplification based on average responses of gravity dams. More things. We need to estimate the consequences downstream that are linked to a peak discharge. So the software is doing that for us, but it needs at least 2 points. One known water pool level, and if the dam breaks at that water pool level, it needs the discharge. So please write down that we know that if it breaks exactly at the crest, the discharge would be 41,282 cubic meters per second. To scale it for different water pool levels and discharge, we use the Froelich equation. The software uses the Froelich equation, but that's not a concern for us. The software does it by itself. So we only need to write down the 1083 correlates to 41,282 cubic meters per second. I think I hear a phone there. So economic consequences, you don't worry about this. Somebody has computed in terms of discharge, the peak discharge. And if the dam fails, it also computes the cost of reconstruction. It looks like this. I'm giving you this in an Excel file, but here is the outflow, and this is the economic consequences if the dam doesn't fail, and this is the economic consequences if the dam fails, because then we have to reconstruct the dam or re-establish the services one way or another. This is given in one Excel file. And the same thing with loss of life. Somebody has done all the simulations, has applied mortality rates, has studied the warning times, and this is how it looks, loss of life as compared to discharge. So somebody has done all these nice computations for us. Then, if we do properly our work, we should be obtaining these results. That the current risk of the dam is a probability of failure of 542 to the minus 5, an economic risk of 4.15 to the minus 3 millions of dollars per year, and a societal risk of 958 lives to the minus 3 lives per year. Once we are in the software and we check that those numbers are right, we will see how to plot them against tolerability guidelines. And then we are doing something more. In fact, I will do one of them, but I will ask you to do by yourself the other cases, which is we are going to consider four actions. And we are going to calculate the adjust cost per statistical life of every of those actions to pick the first one, the one that is more useful according to this risk reduction indicator. Let me talk a little bit about this risk reduction indicator. First, we need an annualized cost of what we do. That means that we need a lifespan, and we need to calculate our investment per year. But that is given in the program. In the program, no, in the statement. So we don't need to worry about that. And then it will calculate the adjust cost per statistical life for us. And the lower the value, the better the action, because with the same money, you save more lives, to simplify the indicator. Of course, all the indicators are very well explained also in the manual of the software, and you are kindly invited to review them because otherwise we couldn't do the exercise. More things. What are the four actions that we are going to check? Let's write down the first one, because the first one I'm going to fully solve it with you. So first one we will do is we are enlarging our spillway. So it will move from 2 gates to 4 gates, and reliability will escalate from 75% to 95% per gate. And the annualized cost over the lifespan of doing this is 0.171 million euros. Well, euros or dollars, it doesn't matter because it's the economic unit that we want per year. You write this down because we will analyze this together. Hopefully we will have time for doing it all well, and then I will ask you to do by yourself these other 3 actions. The other action is refurbishment of bottom outlets. Then you refurbish it, you don't create new gates, but at least reliability of bottom outlet moves from 75% to 95%. And there's the annualized cost of that action. A third action that you can analyze is reinforcing the parapet wall. You can see that parapet wall and making it continuous. So it's kind of heightening the dam by making the parapet wall structural, sufficient and continuous. So that would change the crest level from 1883 from 1083 to 1084.2. And the annualized cost is the one you have there. And finally, I will ask you to check the impact of implementing an emergency action plan, because that changes the loss of life. For the same discharge peak, you will have less loss of life because the warning time increases, and the annualized cost of having the devices, the alarms, etc., is the one I give you there. So what is the adjust cost per statistical life save? Let me explain it because it's an important indicator. It is, on the upper side, you have the cost of your investment. And then you can detach the economic risk now and the economic risk after the investment. And you divide it by the societal risk before the investment, current, and after the investment. And everything is in euros or dollars per year. So you can add, subtract, or divide. And at the end, it is something like the marginal cost of saving one life. It's not that we are putting money to lives, it's that we are calculating the marginal cost of saving one life if we prioritize that investment. This is an important equation to understand. The cost divided by the societal risk reduction gives you the marginal cost of saving one life. So when you do everything by your own, you will have the current situation, then you will have how the probability of failure changes, how the economic risk changes, and societal risk changes for action 1, action 2, action 3, and action 4, and the calculated adjust cost per statistical life. That means, seeing this, that action number 3 would be the one to be prioritized in terms if we use the adjust cost per statistical life, because that means that the marginal cost of saving one life is clearly the lowest, is 2.84, while repairing the bottom outlet gates, in this case, has the higher marginal cost in saving one life. So you would pick action 3 if you need to prioritize using the adjust cost per statistical life saved indicator. So these are the results. If when you are doing the exercise by yourself after I finish of solving very carefully the first one, I will solve today till investment 1. So you will have some homework in doing investment 2, investment 3, and investment 4. So this is the statement. I'm going to review what you need to have handy, which is crest elevation 1083, normal operation level 1077.97, foundation level 1026, return periods of the hydrology from 1 to 100,000, a spillway with 2 gates and reliability 75%, bottom outlet 1 gate and reliability 75%, peak discharge if the dam breaks at elevation 1083 would be 41,282 cubic meters per second. And then we will check if we are doing the numbers properly, and then we will introduce the first action that will be enlarging the spillway, the intake, so that we can have 4 gates, and the 4 gates with a reliability of 95%, and then the annualized cost of that will be 171 millions of euros or dollars per year. It doesn't matter the units. If you have it handy, then I'm gonna escape from this presentation and I'm going to start the software. Any questions so far? Are we good to open the software? Well, what I'm going to do, the software is a little tricky. You have to be very careful. So I would suggest that you do things immediately after me, but not before me. And I will go very slow. I'll try my best. As the session is gonna be saved, if somebody doesn't arrive to the good results, the only thing you have to do is to see again the video and check where you might have made a mistake. But I'm going to go really slow, so when you see the recorded video, if there has been any mistake, you can go back and do it. Okay? I will go very slow. So I'm getting out of the presentation and I'm going back to the software. So first thing, I need to have in a file, sorry about this, you need to have these three files, which I sent you the right ones. Just to make sure these are the right ones, when you open flood routing and you put current situation, it looks like this. And then you have measure 1, 3, and the combinations of 1 plus 3 as different pages in the zip file. When you go to cons econ you have something like this, econ fail, econ non-fail, and it looks like this. I have already explained what it means. And in const lives, you have lives fail current, lives no fail current, but also with measure 4, because it changes if you implement the emergency action plan. You have two sets that would apply to measure 4 or action 4 in our case. So if somebody arrived late, I'm sorry, I had sent you the nice titles, but not the internally were not translated to English. So please download it. You have the link in the chat and you can easily and very fast download them. Now, if you have installed the software, then you can go to your programs and somewhere in your program, you will have iPressas. Let me find it. iPressas it simp. This is our software. And now very important, you have an example in Spanish, an example in English, but don't open those. Then you have a manual in Spanish and you have a user guide in English. That's a good PDF to have. But make sure you open not the example, but the iPressas heatsimp, the one I am selecting, not the examples, because if you open the examples, you are not allowed to change any input data. So we open this third one, and then you should be seeing something like this. Now, what are we going to do? We are going to create our file. Then file, we say new. I press new, and then, as I had explained, I have this basic architecture. I'm not doing anything. I'm going to save it. File save as. Then I go to where you have your files is the ideal place, and then you put a name. I'm gonna say risk in called risk in call. This risk file is gonna be always the same. So whatever name you choose is gonna be the name of your risk file, and it's gonna be uploading different results, but the risk file is gonna be only one. So make sure when you save it, from now on, do always save, not save as. We will do always save because we don't want different names or anything like that. We want one only risk file. Okay, good. Now we are going to upload data to calculate the current risk. And we are going to go very slowly, okay? Floods. I write over there, I just selected it, and it says floods, all the other things we don't need to change, but minimum and maximum return period, we have to let him know. And we had said that minimum return period is 1, and maximum we have available is 100. So make sure you write 100,000 in T max. So from 1 to 100,000. And then the software will be equipped by himself to create all the branches in the event trees, as I had briefly explained you before. Okay? Good. Next one. Normal operating level. We had said that it is 1,000 1077.97. So make sure you write 1077.97. Now the most difficult one. In fact, let's do something. Let's skip this and let's go to routing. So in routing, I want you to go to File, check here, and upload float routing. Upload float routing so that you have uploaded the float routing Excel file and you pick current situation. So you have the link to your file and make sure in sheets you have current situation. And I'm going to open this file from here. Now, very important, also in current situation, you have return period, annual exceedance probability, and you have normal operation level. But you have these other two columns, which is availability of a spillway, ABSP, all capital letters, and availability of bottom outlet, which is AVBO, all capital letters. And these are selectors because you see it's 00, 10, or 20, 01 or 11. So these are the 5 combinations of possibilities with our gates. And they result in different pull levels and in different discharges when the dam doesn't fail. What is most important? That we keep this ABSP, ABBO handy because we'll need to let the program know about the gates, but putting the same name to the gates. We'll see. I'm going to close it. I always say no saving, just in case. So, but do what you want if you haven't touched it. Now we go to gate operation, operability. This is the most difficult one, and where everybody makes more mistakes. Then let's add the spillway first. I click on add and I say, what is the variable? ABSP, the same one that the Excel file in the routing sheet has. How many gates I have? 2. What is the individual reliability? 75%. So I have ABSP, 2 gates, 75%. Well, now I need to add the bottom outlet. Add. What is the name of the variable? ABBO. How many gates or valves? 1. What is the individual reliability? 75%. I'm going to stop here 30 seconds or 1 minute. I want you to check all this part of my screen and make sure you have exactly the same. Because if you don't have this properly, this is going to be a disaster and nothing is going to work. So I'm waiting 30 seconds to make sure you all have time for checking. Good. Routing. I also want you to do something else. In routing, we have uploaded our file, say current situation, but we need to let the program know that we have gates. So in selectors, after normal operating level, I want you to write this sign and then ABSP, this sign, and ABBO. So the software knows that when when understanding the outcomes of the routing, it has to care about the normal operating level, but also the number of available gates at the spillway and available gates at the bottom outlet. The input variable will be the annual probability of exceedance. You don't need to touch it. And the output variables are maximum water level and discharge. But this goes automatically. The most important is that we add these two selectors because not every dam has the same number of gates in the spillway or bottom outlet or whatever. So that's very specific of our dam. So I'm going to stay again 30 seconds and you will appreciate it later because whenever I myself still make mistakes is writing this down. So ABSP, ABBO, and separate it like that. Please make sure you have it exactly as it shows in my screen. Then, on the failure, crest level, we have to write down what was the crest level, which was 1083, and let him know that it is a gravity dam. So it will pick the fragility curve that I have also explained you before. So 1083 and a gravity dam. We don't touch anything else. Everything else is well prepared automatically. Then we go to how to calculate the discharge under failure. And it needs a base level that we said it was 1026. A reference 26, not 28, sorry. A reference level that we said it was the crest, so 1083. And a discharge associated to that level if it breaks. And that discharge was, let me find it myself. It was 41,282 cubic meters per second. So make sure you wrote 1026, 1083, 41,282 there. Now we need to let him know what are the economic consequences and loss of life consequences, either if the dam breaks or not. But we have Excel files that have pre-calculated that for us. So when it says damages, we click here and we have to select cons econ. Open and make sure you select econ fail as a seed. So in damages fail, it will go and select the data of economic losses under failure. Don't touch any other thing. It's prepared to work. So next box, dam damages, but when the dam doesn't fail, we don't have to reconstruct it. So we pick the same file, cons econ, but we select the seed econ no fail. This is done automatically. It calculates the increment. And then we go to loss of life. Then, following the same logic, we open Hans lives and the sheet lives fail current. Remember that with lives, whenever you are doing yourself the action for, you will have to select different values because the warning time changes the results. So make sure you select lives fail current. And in loss of life no fail, then lives and no fail current. So we are basically prepared for running the risk, but I'm going to go once more everywhere to double check we are right. Floods, 1 to 100,000. Normal operating level, 1077.97. Gates, ABSP 2, 75%, ABBO 1, 75%. Routing, SIT, current situation. Selectors, null, ABSP, ABBO. Failure, gravity dam, 1083 crest level. Discharge, base level 1026, reference level 1083, Q discharge 41,282. The rest is good. Here, damage fail, SIT, econ fail. Dam no fail, SIT, econ no fail. Loss of life fail, lives fail current. Loss of life no fail, lives no fail current. Are we good? Well, if we are good, we are prepared to run it. And then we can go here, run analysis, and we have to select a name for the results and for the file where the results will be kept. So call this base case, or yeah, I think that's the best name, base case. Then when you go to results file, click here, make sure you write the same, base case, and then you save it. So you have base case, you have this route to where it's gonna be saved, and you do OK. And then if you have followed carefully everything, you should have analysis finished. Just to know, any one of you didn't get it or got a message of mistakes? If that's the case, you can go back to the recorded video and triple check. But you should all have this analysis finished. Now we want to know if we did it right. Okay, so we accept. We can go to analysis and we can select probability and risk to check if the results are fine. So here, results file, base case, and we need to let him know what is the economic variable and the loss of life variable. So for economic, we have to select econ damage incremental. And for loss of life, we need to select lives incremental. So econ damage incremental, which was calculated by the software in that in the box that I'm pointing out with my mouse, and lives incremental, the same. And then we say, don't need to classify by anything, say calculate. So we can check Probability of failure 5.42 to the minus 5. Good. Economic risk 0.4, let's say 15 to the minus 3. Good. And lives 9.58 to the minus 3. I know there's many numbers there, but roughly, if we round to the third digit, it is exactly what the result should be. But now we are going to analyze it. So good? So far, so good? Now, let me show you things. If you go to analysis and you say show listing and press base case, calculate, you have all the branches. So this is all the branches, all the rectangles where it calculated some little probabilities, in many cases 0, and then everything, maximum pull level, the failure discharge, the lives, everything. So this is not a black box. You can go and try to figure out why the software ended up with 66 branches. And I tell you why. It breaks hydrology in 21 intervals. 21 intervals for the hydrology. I had shown you the example with 10 because it's easier to represent, but the hydrology is done with 21 intervals. Then there's three possibilities of gates running, which is 0, 1, or 2, and there's two possibilities of the bottom outlet, which is 1 or 2. And then you have, sorry, it was still 11. It's not 21 in the hydrology, it's 11. So it's 11 times 3 times 2. Then it's 33 times 2, 66. So it's 11 intervals of hydrology, 3 possibilities of spillways, and 2 possibilities of bottom outlet. So you have 66 combinations, and this is the pedigree of all the calculations. Just for you to know that it is not a black box, that you can follow the event tree if you are interested in reconstructing it. Let's go to something more interesting. Let's go to an FN chart, for instance, here. Let's press it, and then the base case, it's there. So if we plot our risk, which is, this is probability of failure, this is average life of loss, against the US Army Corps of Engineers tolerability guidelines, we are over it. If we do it in terms of capital FN chart, the same. Our box is going too far. So what it says is that some actions are needed. And we are going to calculate the first action, as I mentioned. See that the risk model will be the same. If you go here to the results manager, the base case has been saved. It's here. And now we want to add measure 1 or action 1, which is the one of enlarging the spillway. Okay? But we are changing the inputs, but not the risk model. So if we enlarge the intake, and we have now 4 gates and an upgraded reliability, let's see what needs to be changed. So the hydrographs doesn't need to be changed. The normal operating level doesn't need to be changed, but the gates, yes, because now our surface spillway has 4 gates. I put 4 here, and reliability is very high, 95%. So 4 gates, 95% of reliability. But the routing needs to be also upgraded, and we should select measure 1 for routing. Why? Let me open the file. In measure 1, we have more combinations. If we have 4 gates, it can be 0, 1, 2, 3, or 4 gates working. And we need to compute all those possibilities. And the rest is the same because the overtopping is the same. It's a gravity dam. Because the discharge, if it breaks, is the same, and damages and loss of life are the same because nothing has changed physically downstream. Okay? Then we run it with the new input data, and we call it measure 1. When we say about the file, we call it measure 1. And then we run it. Done. Then what happens? If we now go to our FN chart and we click base case and measure 1, miraculously, it moved exactly over the line. That means that our probability of failure, as we can discharge, we have increased our discharge capacity. We have lowered the probability exactly to the point where it meets the tolerability guidelines. Of course, this is prepared for that, right? But you can see the impact of doing that. If you want to see it in terms of capital FN, you can also do it. Click it here. And again, it nicely enters where the tolerability guidelines say. So what we got with this action is lowering the probability of failure. As you see, the consequences basically don't change, but lowering the probability of failure to a more tolerable area. But we don't know how effective have we been in terms of adjust cost per statistical life. Let me go here. If you go to the results manager, you should have base case and measure 1. Okay, base case and measure 1. Now let's calculate the risk indicator. So you can come here to this button that says risk indicator and press and say, okay, what is the initial situation? Base case. What is the situation once I have done the investment? Measure 1. Remember to change to measure 1. What is the annualized cost of this? We had written it down before, and it was, how much was it? Let me check. It was point something, right? Let me check. 0.171, if I'm right. 171 millions of whatever, euros, rupees, whatever, per year. Then we can calculate all these indicators, but we said we wanted to check ACSLS. Economic damages and loss of life variables remain the same, and we can calculate, and it's 19.51 millions of euros, rupees, whatever, to save the last saved life, which is exactly the number that we were looking for. So what do you have to do now? And I'm going to give you 10 minutes. I would like you to at least calculate one thing by your own. One thing by your own, which would be measure 2. You go to measure 2, which first I'm going to save. Don't say save as, just save. Save. I'm going to reopen the presentation. And now we're going to recall what were the other actions. Which is, this is the one we did. This is very easy one. But remember, you have to come back to the previous situation. You don't add measures. You want to judge this one separate. So, which is, you have to get back your input data to where it was. So this main spillway should be put back to 2 gates, reliability to 75%, and the flood routing to the current state. And once you have done it, you only need to change reliability of bottom outlet from 75 to 95%. Run it, save it as measure 2, and add an annualized cost of 0.029 million whatever per year, and calculate the adjust cost per statistical life of measure 2. I'm going to do it myself, and I'm giving you 10 minutes. And then I will come back with my numbers for you to double check. And then in the last 10 minutes, you can still do the last 2 if you don't want to take homework to home. So I'm going to stop sharing screen, and I'm going to calculate measure 2 and check with you in 10 minutes. Okay? So I'm already working, checking with you in 10 minutes.
उसका वो कर देना सबका वो जो पिलर है उनको फिनिश कर देना पूरा वाले अरे सब नहीं चार जो पीछे के खराब है सबके नहीं करना तो पीछे पानी डाले चार तो पहले वाले सही है पहले वाले फिक्स करना तो पीछे चार नहीं डाले और जो सीढ़ी उससे ग्राउंड कर देना ऊपर छत में वो नहीं चार करके जोड़ देगी सीढ़ी उससे ग्राउंड कर
Okay, can you check in this chat if somebody got the right ACSLS? If at least we have someone getting it right. The ACSLS, that should be 27.5. Before I show how I did it, anyone got it? Nobody got it? Was it that complicated? Or nobody wants to say that?
Mr. Karunesh has dropped his answer in the chat box.
I would be happy if at least one has gotten it before I show it. Yes, measure 2, it's in the Excel file. You will see why. Because you don't need to change anything. It's a good comment, but I will take that comment in my final explanation. Thank you, because Kumar. Anyone got it? Okay, let me share screen again, and I'll show you exactly what you had to do and what is the way of thinking. Okay? Let me share a screen again. I should be sharing the screen. Can you see my screen?
Yes, sir.
Good. So flux doesn't change. Normal operation level doesn't change. Gate operation. You have to put the spillway back to where it was. 2 gates and some problems, because we are analyzing only measure 2. So spillway should be put back to where it was. And what happens to our bottom outlet? Now it's 95% reliable, because basically we are changing the gate, or doing whatever it was required to increase reliability. That's what we do. Okay? In the routing has to be put back to current situation. We don't need to reroute it, because physically we still have 2 gates in the spillway and 1 gate in the bottom outlet. So current situation in routing is exactly the same that if I changed the reliability. It wasn't the same if I changed physically the number of gates. But if I only change the reliability, the routing is the same. Only changes the probability, but the number of cases are exactly the same. So I don't need a specific sheet that says measure 2. And then all the rest is the same. Gravity, the same, the same, the same, the same, and the same. You run it, and when you run it, you should get measure. Oh, it was my mistake. I put measure 3, but it's measure 2. It's measure 2, sorry. And most interesting, I give you 1 minute to run it if you want. Save it as measure 2. Don't do as me, that I save it as measure 3, but it's measure 2. What is very interesting of this is when you go, for instance, to an FN graph, and now you check this measure 2, what happens? As we could expect. Probability lowers, but very little. Why? Because the discharge through the bottom outlet is typically very small compared to the inflow. So even if you significantly upgrade the reliability of this bottom outlet, what this is telling you in risk is that probability of failure is very little diminish. So the measure is very cheap, but the gain in risk is very low. That's why when you come here and you say, okay, I'm going to compare it with measure 2, sorry, by measure 3 was a mistake, then the cost now is very little. Is 10 times less than before, but I buy less risk reduction, and when I calculate it, my ACSLS is higher. That means that this action is less effective than the one we did before. So I think now you are well equipped to do the last two as homework. And I will open the floor in the last 5 minutes. I'm going to stop sharing the screen to, I will stop sharing the screen to any type of comment or question. Let me try to stop sharing if I'm able to do it. Yeah, here. So we have 5 more minutes for any type of comment with regard to doubts, with regard to the exercise, any question on further literature that you want to review. Totally open the next 5 minutes. You can also say if it was too hard, if it was too easy, or if this is what you expected. Anything is welcome.
There is one question in the chat box by Mr. Arun C. Sir, what do you mean by bottom outlet? Is it reverse sluice, canal outlets?
It's not necessarily reverse sluice. It can be the same. Sometimes it gets incorporated as a bottom outlet. Sometimes it's a different intake. So many dams, they have a particular conduit, very deep, to be able to lower the reservoir, even if there's no flood. So it's not the turbines, it's not necessarily the reverse sluice. It's many dams have a particular conduit to control the water pool level. If you need, for instance, to lower the reservoir because you see a crack or because you see a landslide, even if there's no flood or you are not generating energy.
Thank you, sir. Do we have any further questions, query? The participants may ask.
Okay, how we decided annualized cost? You have to do an economic study. You have to see what is the capital investment, what is the maintenance, and distribute it in the span life or the expected life of that investment. So that's an economic study that somebody has to do, accounting for capital investment plus maintenance over a number of years. And the number of years is the number of years you expect the investment to be fully operative. How to create an Excel file? Good, good. Then you have to calculate everything. You have to do the runs and calculate the flood, calculate the consequences, calculate. So basically, if you go to the Indian guideline, you can see how to get all the inputs. But yes, you're right. Getting the inputs is more time costly than computing them. That's why I gave them to you for this exercise. But hopefully the Indian guideline, the DRIP guideline, will if you read it, will let you know how to create those Excel files. more things?
Any more questions?
Hello, sir. I'm Sarabjit Bakshi from Central Water Commission.
Hello.
I hope you can hear me, sir.
I hear you well. Thank you.
The point is, presently I am in charge of this DSM, Director Dam Safety Management. And your training session was quite interesting, I would say, because a lot of new things, the parameters which we need to consider while evaluating all this risk analysis. Yes, we are educated enough. And then towards the end, we had a brief of usage of this software. But sir, I feel uncomfortable because I find there is a gap in my understanding, at least in my understanding, that I have the input parameters and on the other end, I have the software, which I am using it like in what I input it will give something, output it will give. But today I am not in a position to evaluate the results being given by the software. I feel little uncomfortable to find out, like you said, by changing this, we could not find any change in that probability because the sluices and less discharges. Now, I want that I should get myself educated to answer these questions myself. Because I have seen in the past also, sir, I was in designs. So what happened? We had number of softwares. So some people were very good at handling the softwares, doing the modeling and putting the data. But we were, since in designs, we used to do designs through Excel and all. So we could find out what was the error in the input and why the results are coming like this. But at the same time, I was not able to handle the software because modeling, I was not an expert. So here also I feel the same thing. So I just want to learn, how do I learn this? I want to, meet the gaps. How these input parameters are being affected, rather are correlated in the software. Because when I change a parameter X, I should get in my mind that these things will be changed in such and certain modules, because these are interrelated. But that I am not able, though it is, yes, I understand it is 1.5 hour training. It is not possible for us. But I don't find myself in a position to take up a practical problem. I'm frankly speaking, sir.
Agreed. You're totally right. But this was meant to be a short course, like an enlightening course, like opening your minds and to understand the scope of this, not to be in charge of it, because it is literally impossible. It takes months of training to do that. And what is in the guidelines, every page is a lot of effort to fully integrate it in your mind. So that's why trainings are of hundreds of hours to get this. But hopefully, in these 3 hours, you got the idea of what is needed and how could it be used. But 100% agree, this doesn't enable you to be in charge of the inputs or that, and what you feel is totally normal if it helps. But that was the intention of today, just opening the door or the window for see the landscape outside. But that's what we could do in 3 hours.
But sir, we'll be standing at this door or we'll be getting into this landscape and learning this thing. Because that's, this is like a talking superficial and just telling, yes, this sort of thing exists in this world. So you have to contact sir to go further into it.
But it's 3 hours. If you consider what we've done in 3 hours, we could have stayed only explaining the risk equation in 3 hours.
Yeah, that is what my point is. So if that was the aim of the training, just to introduce that something exists of this kind, then I'm quite happy with it.
Okay, that's it's just opening the window to the world of risk. But we can't do more than that in 3 hours.
Oh, that means you require a full dedicated course on this, so as we can very well utilize this software at least. At least we should understand what is happening inside it. Though I am not asking to learn the code, but theory wise, I mean, why?
Yeah,
Why you
for
change
that,
this?
what happens inside the code is not the most difficult. I encourage you to read the manual. You will understand it well. What it would take much more time is to understand how to elaborate all the inputs. That I agree.
Right, sir.
So I'm afraid I have to run for my next meeting.
No, sure.
But hopefully it wasn't painful and it opened a little bit of your mind and interest. And I don't know if from the organization you want to say something.
Yes, if still participants have any questions, query, they may write to the InCold office at sunil@cbip.org or kalpana@cbip.org so that we may arrange your answers through Professor Ignacio and revert back to you accordingly.
Very good. Very good.
So,
I'll be happy.
as for the closing, thank you all the participants for such an interactive and enlightening question answer session. For the virtual training session on the risk analysis applied to dam safety management, I would like to convey my special thanks to our speaker of the day, Professor Dr. Ignacio, for sparing his valuable time for conducting today's virtual training program. I'm sure all the participants have benefited from his vast knowledge shared during the program. Stay safe, stay healthy. Goodbye to you all. Thank you.
Goodbye from Valencia. Bye-bye.
Thank you. Bye.